Yeah, so today I'm going to talk about quantum information theory. And first I'll give a brief introduction with sort of an overview of the sort of questions that we're interested in quantum information theory. And then I'm going to step back a bit and do some mathematical background of quantum information theory. In particular, we're going to talk about density operators and quantum channels. So density operators are basically the quantum version of probability distributions, essentially, and quantum channels are the bread and butter of quantum information theory. We're interested in improving all kinds of properties about them and how much information we can transmit through them. So we're first going to talk about how to define them mathematically, and then we're going to move on to measures of information. So the whole point of information theory, in a way, is to measure information and having appropriate measures of information for various tasks that we're interested in. So we're going to see how to measure information and correlation and so on. And then we're going to get back to some of the tasks that I'm about to talk about in the introduction and see what we can do, what we know about them. And I don't think I'll be able to do a whole lot of proofs, but I'll at least give an overview of the results that are out there. So let's get started. So there's an introduction. The sort of what kinds of questions are we interested in information theory? Well, we're interested in questions such as data compression, encoding over noisy channels. So, for example, in data compression, what we want is, let's say we have some sort of a source of data. So let's say we have a message, and we'd like to compress it into something smaller. So we imagine that we have a message here with a known distribution. Quantumly, this would be a known state. So again, a density operator, which I'll define later. And then we want to compress it into something smaller. In the classical case, it'd be something like a bit string. Quantumly, it'd be a set of qubits. So let's call it C. And then we want a decompressor afterwards. And would like to be able to have something that comes out here, and the decompressor comes out with an estimation of M. And we want M to be the same as what came into the compressor. And we want to, of course, minimize the size of C. Right? So we want a low error rate. If M and M hat were classical, the error rate would be easy to define. It's the probability that M hat is different from M. Quantumly, it's going to be a bit more difficult to define, because what can happen quantumly is, if M is quantum, this could be correlated with something else out there. So this could be some state rho on M here that we're interested in compressing, and some system that's out there, and it could be entangled with whatever's out there. Right? So what comes out here has to take this into account, right? Like if there's entanglement between M and R, we compress it, we decompress it, we want this entanglement to be preserved. Otherwise, we haven't transmitted, we haven't faithfully recovered the state that we tried to compress. Right? So this requires some care to even define what we mean by low error rate in the quantum case. And the second thing we want is, of course, this is compression, so we want C here to be as small as possible. So we want log C here. So C, like absolute value C here, would be the dimension of the system here. The log of the dimension would be essentially the number of qubits that we have in the middle. So we want to minimize the number of qubits here. So as small as possible. So that's one question that we're interested in. So compression. Second big question that we're interested in is channel coding. So here what we have is that, so we have a channel here. So this is going to be some noisy channel here that takes something in as its input. So let's call it A. Produces something at the output called B. And B is going to be a noisy version of A. For example, it'd be something that's, I don't know, takes a qubit in, or multiple qubits, and produces, let's say, with some probability, replaces them by the completely mixed state, with a completely noisy version of A. Right. So this is one possible channel that we could be interested in. And then what we want to do is use this channel to be able to transmit information without errors, which means that we're going to need an encoder, E, and a decoder, D. And again, now we have a message that we want to transmit. So this is, in the quantum case, a number of qubits. In the classical case, it'd be classical bits. And then we want a decoder here. Again, that's going to produce a hat here. And again, we want the same sort of thing here. So we want a low error rate. Again, in the classical case, it's very easy to define. We want the probability of m hat being different from n to be very small. Again, in the quantum case, there's again this issue that we might want to transmit a rho Rm. Let's call it Mr, like I did earlier here. R, with an R system here, and we want to preserve the entanglement between whatever we tried to send and what comes out here. So we're going to have to do some math before we can even define what low error rate means again here. And here, so this is channel coding and not compression. So what we want here is to transmit as many qubits or bits as possible here. So we want the size of m and m hat here to be as big as possible. We want log of m here. As big as possible. So yeah, again, this can be, yeah. So in the case where this is a quantum channel, there are both versions make sense here, where m is either classical or quantum. So we could be interested in looking at how many classical bits we can transmit through a quantum channel, or how many qubits we can transmit through a quantum channel. So both questions are interesting and studied, and we're going to look at both problems a bit later. Another big question that's been pretty important in quantum information theory is randomness extraction and decoupling. And I'm putting both here, two things that look, that sound very different, but they're basically this is basically the classical version and the quantum version of essentially the same task. So I'm kind of packaging them together here. So here what we have is, let's say we have some state rho here. On the AR, let's say. Maybe I'll call it E here. So the idea is that E is so we have a state here that's held, E here is held by an adversary, and A here is held by the participants of some cryptographic protocol. And the idea is that, so this is some state here, and we have our participants that would like to extract something that's completely uniform and independent from A. Like they'd like to process A so that they get something out that's completely random and independent from E. So for example, A could be a bit string that's partially known by an adversary Eve. For example, like in a quantum key distribution protocol, you would get at some stage of the protocol, Alice and Bob have a bit string that they have agreed on, so they know they both have the same bit string, but Eve might have acquired some information about it. So we're in that stage here, and they would like to process A further, so basically make a shorter bit string so that it's independent, so that it's uniform and independent from whatever Eve has. So it's the privacy amplification stage of QKD here. So that's the classical case where A is classical. There's also a version where A is a quantum state and would like to extract something that's purely quantum, or like to get a quantum state that's uniform and independent from E. And how we would like to do this is that we're going to select, for example, a hash function or a quantum channel that we'd like to apply to it. That we select at random here. So we select that. Let's say that's in the classical case. We have a hash function from a set of hash functions here, and then we have a channel here that essentially applies the hash function or applies the channel that we'd like to apply in the quantum case, and then we produce at the output a C here that's supposed to be uniform and independent from E here. So here we have something like this here, and age is something that is announced publicly. So for example, in private simplification, what we do is select a hash function, announce it publicly, and then they apply. Alice and Bob would apply it to their string, get something out of it here, and Eve gains knowledge of age at the end of the protocol. And here what they want is that here, well, let's call this here, let's call this ECH. We want, first of all, that the state here, ECH, is almost something that is uniform here on C. So this is a uniform on C, something that is independent from whatever Eve has, and also from the choice of function here. We want this also to be uniform. So we want something like this here, and of course we have a second requirement, is that we want as many random bits as possible out here, right? If we're doing private simplification in QKD, we want to get as many bits of key out of the protocol as we can. So log C as big as possible. So there are many more problems that we're interested in. I'd like to just focus on these here, and there are various variants of these problems as well that we're interested in. In particular, there are versions of, in particular, compression and channel coding, where we have entanglement assistance. There's one version where assistance. We have versions of these problems where let's say in compression, the compressor and the decompressor, or in channel coding, the encoder and the decoder, to help them accomplish their tasks, they can share entanglement at the beginning of the protocol and consume the entanglement as they complete the protocol. So we sort of give them entanglement for free and see to what extent this helps them achieve their communication task. And it sounds like it's more complicated somehow. It just makes things harder. But for some reason, it appears to make the theory much cleaner. Right? Like we get answers that are much more complete. Like we understand these problems much better, and the final answer tends to be somewhat closer to the classical case. Maybe I'll just copy these diagrams to see how they change. And so we have, let's say, compression here would look like we do compression with entanglement assistance. What it's going to look like is that the compressor will have not only the message that they want to compress as input, but also say I call this entanglement C and entanglement D here. So you'd have things like that. For channel coding, have again something like this here, where again we're going to add entanglement here. So these are just EPR pairs between EA, EB, EA, EB, that the encoder and the decoder can use to help them accomplish their communication task. Yeah, this one maybe doesn't really make much sense. So that's another version where we're going to look at, and as we'll see, the final answers are much nicer and more satisfying, despite the fact that it looks like a more complicated version of the basic problem. And finally, there's the question of any structure that these things might have. So one of the big simplifications that we make in information theory usually is to look at Iid resources. By Iid, I mean independent and identically distributed. So ID, so identically distributed. So basically what this means is that the way I've presented these so far is that we have, let's say, one big channel that we can use, right? Like I've just shown one use of the channel. We have an encoder and a decoder, and it's kind of a one-shot problem here. Same for compression, right? We have one state here that we'd like to compress into one bit string, and then we have to decode one thing out. This is actually, I mean, this is extremely general, right? We could put anything here as the input state. We can put any channel here as the channel, and one of the main simplifications we can make to make the problems a bit more tractable is to assume that there's some structure to the state that we want to compress or to the channel that we're trying to use. And one of the main things we can do to impose structure is to say that the state that we want to compress, for example, is going to be many copies of the same state. So we'd have, for example, row tensor m. So we'd have n copies of our state here. So it's going to be on m1 to n, r1 to n, and then we'd have the rest of it the same, right? So we'd have the compressor and the decompressor here trying to output m hat 1 to n. Have something like this here. So the fact that we have n copies of the same state means that it's already much easier to describe, right? So if we have, for example, if each of these copies is a 1-qubit state and we have n copies of it, then we have still a fairly big problem, right? It's on n copies, but it's easy to describe. So to describe the problem, it's only on one. It's basically a single qubit to describe. Whereas if we look at one big general state on n qubits, already just describing the problem is extremely difficult. It's like exponential in the size of the number of qubits that we're trying to compress, right? So it's going to be hard to get to really interesting answers if we don't impose any structure on the state here. And of course, we could impose more complicated structures here. For example, we could have a markup chain. You'd have n qubits, but not necessarily the same at every position. I think one position might depend only on the previous positions, and so on. There's all kinds of things that we could do here. The same for channel coding. For channel coding, it's maybe even more relevant to look at the IID case, because here the structure that we impose is on the channel here. So instead of having one channel, we're going to have many copies of the channel. Or another way to see this is that we have one small channel that we're allowed to use multiple times. Right? It's effectively a copy of the channel. It's just a use of the channel. So we'd have like n, and again, like we'd have n uses of the channel. So there's n of them here. And then everything else is basically the same. So we replace this one big channel here by n copies of a smaller channel. Maybe I should use these. Let's get it nicer. There we go. The decoder, and then everything else is. So we're still trying to send an arbitrary state here. So here we don't really have to impose a structure on the state we're trying to transmit. Usually in channel coding, we just have an arbitrary state on some number of qubits that we'd like to transmit through many copies of the channel. That's sufficient to get interesting answers. Like we don't have to simplify further. And then at the outside we have again m hat here. And again, of course, we can do this version with entanglement assistance as well. Okay, so that's essentially my introduction. So that's the sort of questions that we're interested in quantum information theory. So now what I'd like to do is to step back a bit and go into some mathematical background here, because some of you might not know how many of the objects I've drawn on the board so far are defined even. For example, like these states here, what exactly do I mean? They're not necessarily pure states. So what you've seen this morning are pure states. Usually what we deal with in information theory are probabilistic objects. So we want essentially probability distributions over pure states. And there's a very nice formalism to deal with these called density operators. And these are what these objects are. Like these are all density operators, unless I specify that they're pure. And the same for all of these boxes here that are like quantum operations. All of these are quantum channels. So completely positive trace preserving maps. So we're going to see what these are, like how they're defined mathematically. So these are objects that operate on density operators. Okay. So let's get started on this. So next page. Mathematical background. So first, density operators. Also known as quantum probability distributions. They're not really known as this, but it would be a nice alternative name for them. Let's put it this way. So what's the starting point here? So suppose that we have a bunch. Let's say we have a probability distribution over pure states, right? So let's say we have let's say we have the state psi I in some Hilbert space with probability pi. Right, so we have a finite set of states here, like the psi's that live in H, and we have a probability distribution over them. So how can we describe them? Of course, we could just describe them by the pair. Like we're going to have the set of pairs pi psi I, and for all I in some set I here, right? Like this would be an option. There's a better way, however, because what happens with this description is that there are many possible ways to describe the same state. Like there are many distributions like these that lead to indistinguishable behavior on the system, and there's a formalism that sort of maps them to the same object. And to see why this is the case, let's say we have this one of these objects here, and let's say we try to measure it in some basis. Basis. Let's say the basis is going to be pi j for j in some set capital J. Right? So this is an orthonormal basis, let's say, and we want to measure in this basis. So let's see what happens. Right? Let's look at the probability that we measure J when we apply the measurement to this, right? Like with probability pi, we have psi. Then what happens is that, well, we sum over I, pi, and have j I squared. Right? Because with probability pi, we have psi I. If we have psi I, then the probability that we measure j is this thing here. Let's write this in a slightly different way. So we have I like j psi I, I, oops, yeah. And now what can we do here? So each of these here, so basically this is a row vector, this is a column vector, this is a row vector, and this is a column vector. We can just view this all as matrix multiplication here, which means that this doesn't depend on I, this doesn't depend on I, which means that the sum here on I could be brought inside this big multiplication. So what we could do is just bring this phi j outside, and then we would get phi j sum over I pi psi I, and then phi j here. And now we basically have the thing we want. So this here would be the object that is going to represent this distribution. So this is going to be we're going to call it rho here. So what is this? This is an operator in like the linear operators from our Hilbert space to our Hilbert space, because as you can see here, it's a convex combination of each of these objects here is a row vector followed by a column vector, which means that if you multiply it by objects in H, it'll spit out another object in H. It's linear, so it's an operator in the space. Call it the density operator. And we can actually say a bit more about the properties of rho, right? It's not just any linear operator in the space. It's actually positive. It's in the positive operators on H. And what this is so the positive operators on H are just the set of operators such that for all psi in H, we have that if we do this here, we get something that's real and positive, and non-negative. And this can be seen pretty easily that this is the case for something that has this form, right? Because if we take any psi here and sort of sandwich the operator in between, we're going to get like the square, the modulo square of something, and then a convex combination of it. Right? So this cannot be negative ever, and this is always going to be the case, no matter what. Like for any distribution like this, it's always going to be the case. And it also has another property that it has trace one. I'm about to show what the trace is, but basically the fact that these pi sum to 1 here is another condition on density operators. And it's going to turn out that any operator that is positive and has trace 1 represents a possible quantum probability distribution. So there's always going to be a set here that represents this, that corresponds to this density operator. So just to do some examples here. So if we suppose that we have the uniform distribution over, let's say, some basis psi I, like an orthonormal basis psi I, then what we have is that rho is sum over so the uniform distribution. So it's going to, so there are, if the dimension of the space is D, then we have D orthonormal vectors in the spaces, and the uniform distribution means that the pi is actually 1 over D, and then we have projector here like this. And if we take this out of the sum here, we have this here, and this is of course a resolution of identity, right? If we sum here over I, this thing over an orthonormal vector, an orthonormal basis rather, then we always get the identity here. And this blackboard bold 1 here is my way of writing identity, just a notation. And this is true for any orthonormal basis, right? So regardless of which orthonormal basis we take, we're always going to get the identity here. So like for example, if we take 0, 0 plus 1, 1, over qubits, this is of course identity. And if we do this the same with plus, 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 minus, minus, we also get the identity. And this is the easiest example of the phenomenon I was talking about a bit earlier, and the fact that there are multiple ensembles here that give rise to the same density operator. Right? If we have a uniform distribution over 0, 1, or a uniform distribution over plus minus, we get the same density operator. And regardless of which measurement we could ever think of doing on them, like we're always going to end up with the same distribution because they give rise to the same density operator. And the distribution that we get at the measurement is always depends only on the density operator and nothing else about this distribution here. So we can sort of forget about the ensemble that was behind and only look at the density operator. And this is what we always do in quantum information theory. And when we're faced with the distribution over quantum states. And if the ensemble actually matters, then we usually specify it by having a separate classical system that is correlated with it. Like we'd have a separate classical system that has the I in it that we have next to it if it somehow matters. If it's not there, then it's simply not distinguishable on the system itself. Another example, of course, is if we have a pure state. If we have a pure state, psi, then of course rho is simply this projector onto psi. Right? And in particular, what this means is that this is the operators of rank 1. Right? Because it has only one. It has one eigenvector, which is psi with an eigenvalue 1, and everything else is eigenvalue 0. Right? So we have an operator of rank 1. And if we have a positive operator of rank 1 that's normalized, that has trace 1, which I'm about to talk about, then we have a pure state that's associated with it. Okay, and so the next thing I'd like to talk about is the trace. So this is another mathematical operation that we're going to use all the time in quantum information theory. So let me just tell you what it is first, and then see what we do with it. So let's say we have an n by n matrix. M, then the trace of M is just the sum over its diagonal entries, right? Like we just sum over the diagonal entries of the matrix M. I'm not going to prove it, but this turns out to be basis independent. So if we do a change of basis over the matrix, it turns out that the sum of the diagonal entries is still going to be the same. So we don't have to. It makes sense to talk about the trace of an operator in the space of linear operators without having to specify a particular basis for the space. This is basis independence. So for any M in like linear operators from H to H without specifying a basis. Another very useful properties of the trace is that it's cyclic, which means that if we have two operators A, B, and we take the trace of the product, it's equal to the trace of BA. And also, even if the trace only makes sense if we take the trace of a square matrix, which means that here AB and BA have to be square, but A and B individually don't have to be. So it could be the case that A is some rectangular matrix, B is another rectangular matrix, but the product is square. Right? That still makes sense, and this is still true. Which means that these are, like, if this is the case, then AB and BA are both square, but not necessarily as the same size. So, in particular, here's what we can do. Suppose that we have, so if we go back to our expressions here for the measurement, so we had the, like the probability of measuring J here on some density operator was bra rho here multiplied by the ket phi j. So we had, let me recopy this here, measure J, which was phi j rho phi j. Now, suppose so this is a number, right? Now, suppose I want to see it as a 1-by-1 matrix. I could easily do that. And if I do that, then the trace of a 1-by-1 matrix is just the entry that's in there. So I can just write it as this. And now I'm just going to use this property here to move. Like I could say that this here is A, this here is B, right? Our column vector here. I'm just going to view it as a matrix. This is a row vector. I'm going to view it as a matrix as well. Now I can swap them around, and I'm going to have, this is the trace of phi j rho. And now this gives us another way of viewing measurements. Right? Instead of viewing measurements as a basis that we measure in, where the probability of getting a measurement outcome is given by this inner product, now we can specify it by operators on the space. So here, this guy here, this is also a positive operator on H. And now I can specify my measurement by the set of operators here that I have in my measurement. If I look at my measurement phi j here, I look at sum here, it actually sums to identity, because if I'm measuring in some orthonormal basis, I'm summing here over a basis in the space. This is a resolution of identity, so I get my identity here. And it turns out that we can generalize this to more general measurements. So basically, instead of having operators of the form ket bra something here, I can just replace them by any set of positive operators that satisfy this equation here. So more generally, can view any set MJ. MJ is a positive operator on H, such that they sum to identity as a measurement. And this is called a POVM, so a positive operator value measurement. POVM. So. Positive operator valued measurement. Because the outcome of a measurement like this is instead of being a J, so it's a positive operator that comes out. The result of the measurement is one of the positive operators in my set of positive operators here. So then the probability of getting outcome mj on a density operator rho is the trace of mj rho. Oh yeah, one thing I forgot to mention as well. We have the trace. One of the main properties of density operators is that their trace is 1. So any density operator rho, we do the trace of rho. It's going to be the trace of. We write it like this here. I psi I. Okay, this is the trace is a linear operation, which means I can take the sum out of the trace here. Psi I, and now I can use again this cyclicity of the trace property here with, let's say, A here and B here. So I swap them around, and then I just get the trace the PI. Then I get the trace of psi I. Whoops. Psi I. This is just 1. This sums to 1, which means I get 1 here. Sorry for the mess on the board here. So then, if we get back to this here, then we can see that this all works out as well. Because if we look at, so this is the probability of getting outcome J, and now if I sum over J over the probability of getting outcome J, getting outcome MJ on when we measure rho, we get the sum over J of trace MJ rho. Again, the trace is a linear operation, which means I can bring the sum inside. Trace of sum of MJ rho. Of course, the sum rho is independent of J. We can do this here. The sum of the MJs here, if this is a valid POVM, we know it sums to identity. So we have this is the trace of rho. And if rho now is a valid density operator, the trace is 1. So we get 1. And of course, this is needed for all of this to make sense, right? Because if we sum over all possible outcomes here, we want to, of course, that the probability is 1.
We just have a quick question from the chat.
Yes.
Xavier asks, do POVMs correspond to some physical measurements? So I guess do all POVMs correspond?
Right. Yes. So the answer is yes. And so in particular, what we can do with POVM, what POVMs cover that this sort of measurements with orthonormal basis don't, are things like, for example, let's say with probability 1/2 I measure in one basis, with probability 1/2 I measure in the other basis. Then I could have, for example, yeah, let's say I have 2 bases that I want to measure in. So psi I and phi j are my 2 bases. Then I could have a POVM where m, let's say mi is going to be psi I. Let's say, and m, what am I going to say? J plus I max, let's say. So I'm going to add a bunch of other outcomes. Oh, yeah, this 1/2. I'm going to add a bunch of other outcomes here. So basically, my set of like my set of operators is just going to be 1/2, like psi1, psi1, yeah, 1/2, I max, psi I max, 1/2, phi1, phi1, okay, 1/2, I max, I max. And this is valid POVM as well, right? So we have a bunch of, so we have more outcomes than the dimension of the space. There's no state, for example, that could produce an outcome, this outcome probability higher than 1/2. But this is of course a physical measurement, right? Like choosing at random to do one measurement or the other is certainly a physical operation. And more generally, I'm not sure I'm actually going to do it, but it will correspond to basically doing any channel and then measuring part of the outcome at the end. So basically, any measurement procedure can be represented as a POVM like this. Like I don't think I have the proof prepared, but yes, like it covers basically any measurement procedure that we can do, even indirectly, by pre-processing the state by any sort of channel and then measuring part of it at the end. Because of course, something else we can do here is to combine outcomes, right? Let's say I have an orthonormal basis, and let's say I only care about, like, I have two subsets of my basis, and I only care about which subset I'm in. So I would just want to measure one bit of it. Then I can group together the two subsets into two measurement outcomes, and then my POVM is just going to be, I measure one of these two operators. Like each of these operators is just going to be the sum of these projectors. Right, like so it covers all kinds of cases like these. And if we want to talk about a measurement in general without having to specify how it's done behind the scenes, then we can just say we have an arbitrary POVM, we measure it. And given any POVM, there's some procedure that could in principle implement it. I hope that answered the question. Okay, so that was the trace and POVMs. Now there's something else that we need is the partial trace. Okay, so now what we're interested in is let's say we have some state on two systems. Like we have a pure state psi, which is in HA, so HE here. My usual notation for this is going to be to write the subsystems here. So like if I write something like psi with AE here, it means that it's in some space here that's the tensor product of HA and HE. So I'm usually just going to write things like psi AE to mean this. And now suppose that we don't care about E. Like just to take a hyperbolic example here, let's say that A here is a single qubit, and E here is the rest of the universe. So for example, and let's say that this qubit is we're interested in this qubit for some reason, and the rest of the universe, well, it's we'd like to ignore it. So how can we do this? Like, do we really want to have a state here that that lives in a massive space here, even if we're only interested in a single qubit? Is there a way to get rid of E somehow and only have something that that only involves A? The answer is yes, but of course it turns out that it can't be a pure state on A. Right? If there's some entanglement between A and E here, there's not a pure state that's gonna do the trick. Right? Like there's no pure state on A that's gonna adequately describe this. what we can do is have a density operator on A that describes everything that happens here. What it's going to be is this density operator is going to be the partial trace of psi when we trace out E. And just to see a motivation of the operation, we're going to see what happens when we try to measure. We apply a measurement only on A here, and so a measurement that doesn't involve E at all. So suppose that we have a measurement on A. So now it's going to be Povm, right? So it's going to be say J, where J is some positive operator on HA. Sums to identity, right? So we have a Povm on A. Let's say we see what happens when we apply this measurement on this guy. So, well, yeah. So let me step back for a bit. So we have this measurement on A now. We'd like to apply it to this state, which means that we need some way of turning this measurement that's only on A into a measurement that's on AE. And what we can do is simply take all of these operators and tensor them with the identity on E. Because let's see what happens if we do this. First of all, each of these operators is positive on HAE. This is not hard to see. If you have a positive operator and you tensor it with another positive operator, you get a positive operator. Identity is a positive operator. And now what you get is that if this guy sums to identity, well, you get that this is equal to the sum only on this tensor identity on E. Then you get identity on A tensor identity on E, which is of course the identity on AE. So now we have an easy way to turn a Povm that's on A into a Povm that's on AE. And now let's see, I look at what happens when I apply this measurement on a state that's on AE. I'll have, let's say I look at the probability of getting J, right? Getting outcome J, trace of NJ tensor identity psi. And now, one thing we can do is that the trace here is basically sum over all the diagonal elements. Like I said, it's basis independent, so I can choose the basis on AE over which I do this. And one possible choice is always a tensor product basis. So I can choose a basis in which I'm summing over an index that's on A and an index that's on E. And so let's say I can sum over AE. I think this is indexing. This is a basis for A and a basis for E. This would be like A. So E. Okay, so for the trace, one way to write the trace, I defined it as the sum of the diagonal elements of a matrix, and one way to write this is like this here. So you would have like ket I here would like the ket I here would be some orthonormal basis. Again, it's independent of basis, so we can do this with any basis. And then you can just sandwich it between a column vector. That's the column vector, the row vector. This is going to pick out the diagonal element labeled I if you write the matrix in that basis. And again, if we get back to the expression we were computing here, which was the probability of getting outcome J here, if we apply a measurement on A alone, but on a pure state that's on AE. So we had that we found out that the POVM element was this, like, take all of the POVM elements on A and then tensor them with identity on E. And now one way to, let's use this expression. Let's choose a basis that's a product basis between A and E. So now we're going to sum over A and E here. And each of these I here becomes A tensor E. And now we're going to have this guy here. So MJ tensor I psi, and then A tensor E. And now what I'd like to do is, so this here is only on A, so I'm going to leave this get A outside here, but I can move the E's here inside the expression here. I don't have to. We can move them inside the multiplication by M here, by MJ. So we're going to have some A here. Then we're going to have MJ. No, not tensor I. Right. So if I move this inside here, I'm just going to have identity on A tensor E here, like the bra E here is going to get moved in here. I'm going to have this thing here, and then again I'm going to have identity on A tensor E, and then I leave A outside. So now let's look at oh yeah, then I have the sum over E here that I forgot. So now let's look at this object here. So now I have this here is good. This here you can view as an operator from A to AE, right? HA to HAE. So I do an identity on A and then I tensor with something that's only on E. Now I have an operator on AE, and then I have an operator from AE to A here. So now this whole thing here is an operator on A alone. So this is on L, HA, and this here, if you we have this big operator on H. This operator, I'm going to call it rho A. Rather no, I'm actually I'm going to call it trace E of psi, which is in this thing here. So this is how I'm going to call it, and then this here I can go back to calling it a trace, right? Because now I have the sum over A and A here is just the trace over the whole system, and then I have MJ here that acts only on A. Right? So I have trace of MJ, then I have trace E psi. And now I have my density operator on A alone. So this is the object we were looking for, right? So we had our pure state on AE. We wanted to only care about A, which means that we wanted a mathematical object that's only defined on the system A. That tells us everything that we need to know. For example, when we apply a measurement on it, we want to get the right statistics, and so on, without having to care about E. And this is the object we wanted. This density operator on A contains everything we need to know to be able to compute the probabilities associated with a POVM that's applied on A. Right? So now, if we have a description of this guy that's only on A, we don't have to. We can forget about E entirely if we're only doing measurements on A, and it's going to be the same if we do something other than a measurement. Like if we do any channels or anything else that we might be interested in doing with it, as long as if E is not involved at all, then all we need to know is this density operator. And this operation of transforming this state on AE into a state on A alone is called the partial trace. Hence the notation here. We're tracing out E, like kicking out E and leaving only E. Kicking out E, leaving only A. Sorry. And of course, it's essentially just the same as the trace, except we're applying it as part of a bigger system, right? Like the operation is still just summing over a basis here, except that we're tensoring with an identity on the other system that we still want to keep around. And of course, this final trace here that we have, we could also call it a partial trace on A, except there's nothing left, so it's just a trace. So the trace on AE is really the trace on A and the trace on E, one after the other. So that's what I had to say about the partial trace. The next notion that I want to introduce are quantum channels. So far, I guess we've seen unitaries, right? So that's the transformations that we've seen, and let's say we have if we assume that everything we can do is unitary, right? Like this is usually taken as an axiom in quantum mechanics that everything is a unitary operation as long as you make the space big enough. So what can we do when everything is unitary? Well, and let's say we have a state psi A here in HA. What sort of operations can we apply to the state? Well, we could consider it as part of a bigger system. So we could place it next to some other state that I'm going to hold psi 0 in some other space. Right? I can always say tensor. We'll call it ket 0 in A prime. And then I could apply U. I could apply some unitary on A prime. And once I apply the unitary, maybe you can split the space in a different way than just A and A prime. For example, if A is a bunch of qubits, A prime is another bunch of qubits, I apply a unitary, and then let's say I want to split the qubits in a different way, right? Like I want to keep a smaller number of qubits as part of another, as part of one system, and more qubits as part of the other system. So what I could do is that you could have the spaces HA prime, which are isomorphic to, let's say, a different way to split the system. So this could be the case, which means that you could have a unitary which goes from A prime to BE. You can always, if I have this equivalence between the spaces, I can always have a unitary where I also relabel the output space like this here. So this is a valid thing that we could do. It's going to be in HB answer E, and then maybe I don't care about E, right? So another thing I can do after applying the unitary is this partial trace on E, because this is not really a physical operation so much as a change of point of view. But there's still E around, but I don't care about it. So I can always apply this trace. It's just a mathematical operation more than a physical one. The physical operation was U. So can we represent this whole operation in a more convenient way? Right? Again, suppose I only care about what happens to A, and I only care about the output system being B, right? Like I want to view this whole operation of adjoining ket 0, applying the unitary here and looking at what happens to B as one big operation, like I'm doing something on A, and what comes out is on B. Can I describe it again in a way that only involves A and B without involving this A prime system or this E system, which could be much bigger than A, right? Like again, you could imagine that A is a single qubit, and A prime could be some huge system that it becomes that it interacts with briefly as part of this unitary that I don't care about. So, and I'd like to have a description of this whole operation in a way that A prime doesn't get involved in the explicit way, or at least no more than it has to. And again, maybe this is not pure either. Maybe I only have a density operator to begin with. Right? So what I'd like to have would be something like I have a density operator on A. Let's say this thing, and now let's say I apply this operation to this density operator. Right? Like now it gets even more complicated, right? Because let's say what happens here now is that I applied this unitary on. Well, I first tensor with 0, and then I apply the unitary on each of these states here as part of the decomposition of rho here. So what happens is that this becomes U psi I tensor 0, and then I have to do the same thing I have to do the conjugate transpose of everything here. So I have something like this here, then I have U dagger here. Can I write this in a slightly more convenient way? Yeah, so one thing I can do is get the U's out of the sum. So I can have U here. I'm going to have over Pi of I. I can put the zeros together here. So this is the first part of the operation, right? The part that involves U, and then I want to get rid of E. Right? I'm still interested I'm interested in not in being interested in E. So I want to trace out E. So now what I get is trace of E of this thing. Right? So trace out E, U of I. Zero, zero, dagger. And now I'd like to get to a more convenient description of this whole thing, right? That doesn't involve a U that has A prime and E here. So I'd like to get a smaller mathematical object. So again, to see how this would be possible, I'm going to write out the partial trace on E here explicitly as a sum over let me call it E again, like I did earlier. So like this here. Now I have U over. Now maybe I'm gonna put this again. Here. Should I write this? Yeah. Just gonna write the expression and see how we got there afterwards. 0. Note that here this is rho, right? We had rho A. We had this here U dagger, and then I still have the other E here. And now I'm essentially where I want to be, except it's maybe not so obvious now, because so now I have my I have something that looks like something being applied to row here, right? Like I have my row in the middle. This is what I care about, and then I have this big operation applied to it. And now let's see let's look at these guys here. So this is an operator that goes from A to A prime, right? Because I take in something in A, I tensor it with something in A prime. So this is an, I'll write it out. This is an L HA to HA tensor HA prime. This guy is an L HA prime to HB HE. This goes from HBHE into HB only, because we're getting rid of it because of this bra E here. So the combination of this of these three objects is a linear operator from HA at the right here into HB. And I'm going to call this NJ here, NE rather. Change this compared to my note. I'm going to call this NE here, and this thing here is NE dagger. And now I get a much nicer expression, because I have the sum over E of NE rho A NE dagger. And now this is basically the expression we wanted here. Let me write this nicer. Because now I have something that doesn't involve A prime or E explicitly. I just have I have my density operator on A alone. I have these operators here that only involve the two spaces I'm interested in, HA and HB, and nothing else. And then I just sum over a basis for well, I sum over a basis for E, but I can just occult the fact that this is anything, right? This is just a sum of a bunch of operators on this here. And it turns out the number of terms in the sum cannot be too big. So now what we're going to call a quantum channel is basically anything of this form. And basically any physical operation is going to correspond to an object like this. So what do I mean by an object of this form? Well, it does have a few properties. So we can note that, suppose that we look at NE dagger NE. Let's write it out. So NE dagger is this guy. So rho U dagger IB tensor E. And now NE U Now, what is this equal to? Well, we have a sum over E here. The only things that depend on E here are inside here. So it's just this guy and this guy that depend on E, which means I can bring the sum inside and get this U dagger. Identity on B is not involved in the sum either, so I can just bring the sum inside that thing too. So then I have sum over E of E U IA answer 0 Now this, of course, get E is an orthonormal basis for E, so this is a resolution of identity. Now I have one big identity here. I have U dagger U. Of course, it's unitary, which means that these guys go away as well. They cancel out. And then, of course, I get bra 0, get 0 on A prime. Again, this is just 1, so this goes away. And all I get is identity on A. And this is basically this is the property that we need here for this to be a valid channel. Like this has to be true for a channel. And it turns out that any expression of this form, so a sum of operators like this, with the dagger on the other side, such that this expression here sums to identity, is a valid quantum channel. So it corresponds to a valid expression. You write it. This is a quantum channel. Usually you write it as use the notation I was using in the introduction. Like this is mathcal n. Would be something of this form. So sum over. Maybe I'll get back to the notation I have in my notes with the J, such that J dagger sums to identity. And this is also called a Cptp map. This is for completely positive and trace preserving. So completely positive essentially means that suppose that I have an operator x that's positive. So this was positive operator on let's say HA, and suppose that I or actually on HA, tensor, let's say so maybe on some other space as well, R, and I apply n tensor identity on R to X, then I get something that's positive on HB, HR. So positive, like if I remove the completely here, it would just be the same condition, but without the HR. Completely positive means that it remains positive even if I tensor it with the identity on some extra space. And this is really needed physically, because if I have my channel here and I apply it to something that's, and there's some other reference system here, rho here is supposed to be if I input the density operator, it's a positive operator. If this is to be a valid channel, this better be a positive operator as well, because it's supposed to be a valid density operator, which means that it needs to have this condition. And trace preserving means that, of course, the trace of I do the trace of n of x for some x in J, then this is just the trace of x. And again, this is needed because if I input some density operator rho into my channel, a density operator has to have trace 1, which means the output, if the output of the channel is also to be a valid density operator, then it better have trace 1 as well. So the trace at the output better be the same as the trace at the input. And it turns out that these two conditions characterize completely everything that we can do physically, right? Like if we have a map, so if we have a map n from linear operators on HA into linear operators on HB that satisfies complete positivity and trace preservation, then it's a valid quantum channel. It's a valid physical operation that we could apply. So maybe I'll do some examples of this, of quantum channels. Some of the more relevant examples for quantum information theory, so some of the basic channels that we look at. First one is the erasure channel. So an erasure channel is basically a channel where I send in my system, and then with some probability it comes out unchanged, and with probability epsilon you get an erasure flag out of it. So what comes out is something like it's a vector that was not in your initial space. It's basically a state that says I lost my qubit. Do you assume that your Hilbert spaces are finite dimensional? I'll just assume everything's finite dimensional here. I'm the worst person to talk about continuous variables. Most of what I talk about is valid in continuous variables, but maybe I'll say something that's not true in infinite dimensions. So I'd rather not. Let's just assume here that everything is finite dimensional in this talk. So now the erasure channel would be n rho here. So with some probability, well, with probability 1 minus epsilon, let's say I get my rho back. And with probability epsilon, I get some state here that was not in my original Hilbert space. Right? That says there was an erasure. Now this does not look like the expression I wrote earlier. Right? It doesn't look. It doesn't seem to be of this form here, and it looks nice when it's easier to interpret, right? Because if you look at the density operator here, it looks like exactly what I'm saying, right? Like 1 minus epsilon rho, like with probability 1 minus epsilon, you get back rho. With probability epsilon, you get the erasure flag. If I want to put it in this form, I can certainly do it. Like this here would be something like 1 minus epsilon square root identity rho identity, and then plus, and now for the other one, I can always do something like square root of epsilon. And now I'm going to sum over some basis for the space here. Rho I square root of epsilon here. So now it's in the form of this here, right? Like I have a sum here where each of these here, like the square root of epsilons times this thing, is one of the ni's. This is the remaining ni here, like this. Right? It's not hard to see that this is equal to this. There's also the depolarizing channel. And the depolarizing channel is a bit like the erasure channel in the sense that with probability 1 minus epsilon, you get the same state back, except now with probability epsilon, instead of getting an erasure flag, you just get a completely random state. So you get a maximally mixed state at the output. So this would be, and rho is equal to, again, 1 minus epsilon times rho plus epsilon times identity over d. So this is the maximally mixed state. So it's basically a uniform distribution, the quantum equivalent of a uniform distribution. I'm not sure if I mentioned it earlier. Again, if I want to put it in the form in this form here of a quantum channel, I can always write it like. Well, again, I can do the same trick here for this part. Minus identity rho 1 minus identity this here plus then I have this, I can always I have to turn everything here into the identity here. So what I can do is this, rho plus x, rho x plus y, rho y plus z, rho z. I'm not going to do it, but this turns out to completely randomize rho here. And now, this is identity. And again, I can put this factor here inside these operators here, and then I get something that's in this form here, a sum of a bunch of like these, like the x, y, z's here are going to be the ends, and then I have an extra one here.
We have a question.
Yes.
Raphael says, the main difference between the erasure and depolarizing channel is the fact that the erasure channel is unitary while the depolarizing is not.
No, so that neither of them is unitary. So a unit, the easy way to see this is that a unitary channel is doesn't lose anything, right? You can always reverse it. Because if your channel is unitary, it'd be something like this. It'd be something like, right? Like a unitary channel would be a channel where you only have one term in our sum, and the one term, the end of the one term is a unitary, like this. So this is a valid quantum channel, and of course this you can always reverse by applying U dagger to it. And there's no chance of doing this with an erasure channel, right? Because once you get the erasure, there's no way to get back. There's nothing is gonna get your state back. So there's no way to express the erasure channel as a unitary channel, right? And the same for the depolarizing channel. This is also not unitary, because again, this is not a reversible operation. From the output, there's no way to get back to the input. At least certainly not with probability 1. So they're both noisy channels, just in different ways. I'll have another question. So is unitary equivalent to the fact that n LHA to LHB is bijective? No, I don't think so, because I think you can have, because if you have an n that's bijective but not unitary, it's not going to be reversible, because then you would end up with something that I don't know if I can come up with a simple example here where you could imagine maybe having something where you have one of the nj's that would be something like maybe 1 and then like 1/2 or something like this, and then other terms that do this. So this is certainly invertible, right? But to get back to it, you would need something that violates this trace preserving condition. Like you wouldn't be able to get something that's identity out of it. Right? So you can have terms, you can have n's here, elements of this here that are invertible, but not necessarily unitary. And this is still, as a channel, it's still not going to be invertible. Like it would be invertible, but by an operation that's not physical. I think Guillaume has an example in the comments. Okay, so that's basically what I had to say for now about quantum channels. The next concept we need are purifications. So now this is sort of the inverse of a lot of things that I've been talking about in the past half hour or so. So far we've been interested in we had a big operation, and we wanted to ignore part of it. Now we want to do the inverse. I suppose that we have some let's say a density operator. Can it be represented as a pure state over a bigger space? So this is the inverse problem from the one where we had a pure state and we only cared about part of it. And it turns out that this is also the case. Like if we have a density operator, you can always view it as a pure state on a bigger space, such that if you take the partial trace, you get back the density operator that you have. So suppose we have rho A. Turns out that there exists a purification. So the purification is going to be a state on a bigger system. So I'm going to add a system R here, such that trace out R psi, I get back rho. And the way to see this is to use a rather neat trick that involves the state phi here. So I've been writing this quite a bit. So this is a maximally entangled state here, and I haven't really defined it. So I'm going to define it now. It's just this state, dA square root of dA, and then I have I tensor I on A and on R. So this involves two systems that are of the same dimension. So here I suppose that A and R have the same dimension. It also implicitly involves a choice of bases for the two spaces. Right? Like this is not basis invariant, this state. If I do a unitary on one of them, like I basically have to make a choice for the basis on A and on the basis on R. So whenever I write this, there's always a choice of basis that's there in the background. One of the main properties of this state is that if I trace out R, this thing, I get a maximally mixed state on A. So this you can work this out yourself. This is going to be true. And now the trick that we're going to use to construct a purification for a given rho A is the following trick. So if we have some operator L X on HA, so it's any linear operator, and I look at this as phi AR, if you work out the math, this actually turns out to be equal to IA tensor X R transpose phi. I mean, to see this, you just have to write it out with the indices and slug it through, and it's a calculation. It's not hard. It's just maybe a bit tedious. And of course, this transpose here is done in the like the transpose is basis dependent, and it's in the basis that was used to construct phi. So we have a transpose that's compatible with this basis choice that you had here. Actually, do I need this? Maybe not. Anyway, so now we're going to use the state to construct a purification of rho A. Right? So given rho A, we're going to construct psi AR. The following: so dA square root. Now rho A, the square root of rho A. I'm I'll say a few words about this in a second. By AR. And what do I mean by this? And this might look really weird at first. All I mean by this is that, so suppose that rho A is this density operator, so this is the spectral decomposition of my density operator. So this is an orthonormal basis. And suppose I have a function f, it's a function of real numbers. Then when I write f of row A, all I mean is I'm applying f to the eigenvalues of my operator. So in particular, if f is the square root, then I'm just writing a row like this here, and I'm putting the square root, like I'm square rooting all of the eigenvalues of it. So this is what I mean here by square root of A. And now I claim that this is a purification of rho. And how can we check this? Well, to check this, we have to check that this is true, right? That the trace of R of my state here is in fact rho A. So let's do that. Trace A of trace R of psi equal to trace over R of now I have the A rho A tensor I R phi rho A dagger, but this is a Hermitian operator, so it's don't have to do the dagger. Then square root of dA. So now those square root of dAs here, that's just a number, so I can take it out. And now notice that these guys here are on A. I'm doing the trace on R alone. Remember that the trace on R is just a bunch of things that only involve R here, which means I can move it inside. I can move it inside these square root of A here. So what I have is that I'll have square root of rho A, trace R, this guy, square root of rho A. And now, like I said, the trace over R, the partial trace over R of this state here is the identity over dA. So now I got A square root of A, identity over A, dA, A. And now these guys go away. If I multiply the square root of rho A by the square root of rho A, so if I write it out like this, I'll have that. Basically, I'm squaring all of the eigenvalues individually, so I get back rho A, in fact. And so this is a purification of my state. And of course, I can do this with any state at all. So given any density operator, I can always find a purification for it using this trick. There's also a fact, which is that all purifications are equivalent in the sense that there exists, given two purifications of the same state. Right? So there's two purifications, psi AR, phi AR of rho A, then there exists a unitary on R such that, you have a unitary that converts between the two. And so that psi AR is equal to U, identity on A, tensor U on R of phi AR. So effectively, the only choice I have when defining a purification here is the basis that I choose on R here. I can play around with what happens on R, which makes sense because I can just ignore whatever I do on R will not affect what happens on A, right? So if I have a purification, I apply unitaries on R, certainly won't affect the density operator on A, and this is essentially the only thing I can do. There's no other purification I can define that's not the standard purification with a unitary applied to it.
So there's a question in the chat.
Yes.
It says, I'm not quite sure which R you are choosing to do the purification. Is this any system?
Right. So this is any system that's big enough. So what I need here is that this state has to be defined, which means that R has to be big enough to contain a basis, or like I have to have enough space to put all the i's here in R. I could of course take a space that's bigger with an extra space I'm not using to define it, but otherwise, yeah, there's no restriction on it. Here, just to make it convenient, I'm just assuming that R has the same dimension as A, but this is not needed. And in fact, these two purifications here, I put it on the same system, but I could have two different spaces here. The only restriction, again, is that both of them have to be big enough, which means that they have to be at least as big as the rank of row A. And then to convert between them, you're going to have not a unitary, but a partial isometry, so something that converts between the two spaces. So if you have R and E, you'd have a partial isometry from R to E. Okay, so the minimal size of R is the number of pure states inside the original density matrix. Am I right? Yes. Yeah, that's right. That's right. So the smallest it can be is the rank of row A. Okay, and now, and I'm really running out of time. But one sort of last thing I want to do before getting into at least information measures is the same thing for channels. So now we've looked at purifying states. We can look at purifying channels as well. And so we had our description of channels that only involve the input system and the output system, like this here. And this we derived from a representation that involved having a unitary on a bigger space. Can we do the reverse process again? So if we have a quantum channel, can we come up with a unitary on a bigger space that does the same thing? The answer is yes. It's called the Stein spring dilation of a channel. So purifying channels. So now suppose we have a channel, channel N, from A to B. So it maps row A to N and I, row Ni dagger. Then there exists a partial isometry V. So basically, when I say partial isometry, you can think of it as it's basically a unitary that potentially expands the space. Such that just so because I don't want the output to be A necessarily. I want to be able to go to something bigger. So and rho is trace of E of V rho V dagger. If you want it to be a unitary, you can do what I did earlier with the A prime here. So basically, you add something bigger here, A prime, to make it as big as BE, and then you have a unitary. It's just that then this way you don't have to have the ket zeros hanging on A prime hanging around. It's a bit cleaner. And to see why this is true, we can construct a V from the NIs. So V is going to be sum over I of NI tensor ket I on E. So I claim that this works. let's do the computation. So trace over E of V row V dagger, which is trace over E of I J is there J here. So that here I just plugged in this V here, and now let's write out what happens here. So if I do the trace on E here, this means that I'm gonna do a sum over, let's say, K here, and now I'm gonna have right, I'm gonna have K here on E. This guy's on E. This guy's on E here, which means that yeah, maybe I'll make this a bit shorter. I have this guy here and K on E, and then what happens is that this K here is going to be multiplied by the I. This K here is going to be multiplied by this broad J here, which means that now I'm going to have my three sums here, and they're going to collapse into a single sum over I, because all the terms where K is different from I or K is different from J is going to be 0. So here this is going to be sum over I of, whoops, the point is I get rid of the sum, and I row and I dagger. And this is what I wanted. And so this is, so the V here that corresponds to N is called the Stein-Spring dilation of the channel. Get to actual information theory. So now one last thing I want to talk about before getting into real information theory is distance measures on quantum states. Distance measures. Actually, I think I'm only going to talk about one of them. I'll skip the fidelity. So given two, let's say we have two states, so two density operators, rho A and sigma A, two density operators. So how close are they? Okay, is there a natural distance measure that we can have on density operators? And of course the answer is yes, and the main one that we use in information theory is called the trace distance. The trace distance that we usually denote like this. So it's actually also a norm on the space. So it's called the one norm also between them, and it's defined like this. So it's the trace of, then I have the absolute value of the difference between these two things. And again, what do I mean by the absolute value of these things? It's again this trick that involves it's this sort of thing, right? If I'm applying a function to an operator, I mean I do the spectral decomposition of it, and then I apply the function to the eigenvalues. And here's the same thing, right? So I have a difference of two operators. It has a spectral decomposition, so it has a bunch of eigenvalues, and then I will apply the function to it, which is the absolute value to it. So basically, this is the sum of the absolute value of the eigenvalues of the difference between rho and sigma. So that's how it's defined. Why do we use this in particular rather than some other distance measure? The main one is this fact that I'm not going to prove, which is that it corresponds to the guessing probability of the following game. So suppose that I have a box that produces a quantum state that's either distributed according to rho or according to sigma. So basically with probability 1/2, it spits out the state rho. With probability 1/2, it spits out the state sigma. And now suppose that I have this box, something comes out of the box, and now I have to guess whether it was rho or whether it was sigma. And it turns out that the best probability of winning at this game by doing a measurement, right? Like whatever comes out of the box, I do a measurement on it, and then I make my guess based on the measurement results. And the best the best probability of guessing this game is 1/2 plus 1/4 rho A minus sigma A 1. And it makes sense, right? Like if rho is equal to sigma, so basically if whatever comes out of the box is exactly the same thing, whether it's rho or sigma, then I have no chance of doing better than just flipping a coin and answering, and then I win probability 1/2. And then of course the trace distance is 0. If they're completely distinguishable, let's say rho A is ket 0 and sigma A is ket 1, then if I look at the trace distance here, then this is going to be 2, right? Because I'm going to have 2 eigenvalues, like one is going to be +1 and the other eigenvalue is going to be -1. So this is going to be 2. Then I'm going to have 1/2 plus 1/4 times 2, which is 1. And of course, if you're somewhere in the middle, then you get an answer that's somewhere in the middle. And why do we care about this particular game? Is that a lot of the times in information theory and also in cryptography, what we do is that our measure of success is going to be the trace distance between one state is going to be what comes out of the actual protocol that we're doing. Let's say I'm sending through a channel, and then I have a decoder, and then I have a state that comes out at the very end. And sigma is going to be the ideal thing that we want from the protocol. So let's say I'm doing channel transmission, then the ideal thing I want to come out of the protocol is exactly the state I put in at the beginning. And then if I look at the trace distance between the actual protocol and the ideal version of what should come out of the protocol, and suppose that it's essentially indistinguishable, then I'm happy, right? It means that if I use this protocol as part of a larger thing, right? Let's say I'm using a protocol to send through a quantum channel, and now I'm going to use whatever comes out of this protocol to do something, right? Then whatever I do, if this trace distance is almost 0, that means that anything I do afterwards with the outcome of the protocol is going to be indistinguishable from the case where I had the ideal thing, because the best probability of guessing is almost, you almost have no advantage of guessing between the two, right? Including if you do some other complicated protocol at the end, and then see what comes out of the bigger protocol. So this is why we like the trace distance in information theory, and the same in cryptography. There's always this, we look at the distance between the real protocol and the ideal version of the protocol, and then the fact that it characterizes the probability of guessing, means that we can't even tell it apart from what we want ideally. So it's a very strong guarantee. So this is why we look at this distance measure instead of another one. Because there's all kinds of distance measures that we could define. Okay, maybe I'll skip some of the other stuff I had here. So there's another distance measure that's used a lot called the fidelity, which I'm just gonna skip. So instead, I'm gonna go into information measures. So now, to do information theory, we need a way to measure how much information there is in a quantum system, or how random something is. And one way to do this is, well, To do this, we're going to step back a bit and look at the classical case first. Right? Like, let's forget about quantum for a second and just look at a classical random variable. Like suppose we have a classical random variable and we'd like to quantify how much randomness is present in this random variable, or how much information is present in it. And one way to do this is to first look at how surprising an event is. So, like, how much information is contained in the fact that an event happens. So the first thing we can observe is that if an event is almost certain, like let's say the sun is gonna rise tomorrow morning, and we learn this fact, right? Like the event happens, and we learn that it happened. We learned essentially nothing, right? Because it's something that we basically knew beforehand that it would happen. So the fact that it happens doesn't tell us anything in particular. Conversely, if something is extremely surprising and it happens, then learning that this happened gives us a lot of information somehow. Right? And to quantify this, we can define the surprisal of an event. So this is something Claude Shannon defined back in the 40s. So a lot of the stuff I'm going to talk about the basics of information theory and information measures and entropy. This is basically Claude Shannon back in the late 40s that came up with all of this essentially all at once, more or less. So the surprisal of an event here. So this would be we'd like to ascribe to put a number on how surprising an event is. And there's a few considerations that we could impose on this to come up with the right expression for it. Like for example, we'd like to measure this in bits. Somehow we'd like our final measures to be in bits. So one natural way to do this is to say that if an event has probability 1/2, then its surprisal is going to be 1 bit. Because then it essentially means that if we learn the fact that one particular bit is 0, like if you have a bit that's uniformly distributed, and you learn the value of that bit, that's an event, then we'd like to say that you learn 1 bit of information. Or if you learn a totally random bit string, bit by bit, then each bit is going to correspond to an event that occurred with probability 1/2. So if you learn the value of an n-bit string, then you've learned n bits. And other considerations would be things like if the less probable an event is, then the more informative it is. Another thing is if you have 2 independent events, then the surprisal of the 2 events of the 2 events happening at the same time should be just the sum of the two surprisals. Right? If you have 2 bits that are independent and you learn the value of each of them independently, then you want the surprisal of this to be 2 bits somehow. Right? And there's a few other technical considerations, like you want it to be continuous, like a continuous function of the probability, and so on. And there's a way to develop this axiomatically. I'm not going to do it here, but the upshot is that the definition of the surprisal would be like the surprisal of an event E would be defined as minus the log of the probability of E. So for example, like again, if the probability is 1/2, then you have minus the log of 1/2, which is 2, right? This is whenever I have log, this is log based. And now that this gives us a way to measure the surprisal of an event, we don't really talk in terms of surprisals all that often. What we really want in the end is a measure of how much information there is in a random variable, and not necessarily in a particular event. Like an event would be the event that the random variable takes a particular value. So to do this, well, one natural way to define the amount of information in a random variable is to look at the expectation of the surprisal of the event of the random variable takes a particular value. And this is basically the entropy. So this is going to be the central definition here. The entropy of a random variable. So let's say you have a random variable x, and its entropy is denoted by h of x, and it's going to be the expectation for x of the surprisal of the event that x takes value small x, and then I guess small x is distributed according to this probability. So here there's a like px here is a probability distribution over x. Over, let's say, x, like script x being the set over which x takes its values. And of course, if we work this out, this is sum over x of the x of x, so this is just the expectation, and then we plug in our definition of the surprisal here, which would be minus log and then p x of x, right? The probability that x takes value x is just p of x. So we get our definition here of the entropy. So again, if x is a single bit uniformly distributed, then it has entropy 1. And then if we actually look at this special case here of a single bit distributed, let's say p of 0, let's say for a single bit, p of 0, and then if we look at h of x on this axis here, it looks something like this. To have an idea of what it is, right? So if p of 0 is equal to 1/2, then we have an entropy of 1, and then it goes down to 0 symmetrically as p of 0 goes to 1 or to 0. Because if we know that x is always equal to 0, then you have no uncertainty about the variable, the same if it's always equal to 1. And the other simple facts. So if of course the entropy is always non-negative. So of course you're taking an expectation of something that, like the surprisal, is always minus the log of a probability. So this is always positive. So you can never go below 0. It's a bit harder to show, but this cannot be bigger than the log of the size of the set over which x takes its values. So it's always bounded between these two values here. There's a conditional version of the entropy. So this is basically the entropy. So if we have two random variables x and y, and we'd like to know the entropy of x from the point of view of someone who has access to y, this is basically just going to be defined as the expectation over y, over small y, let's say, of the entropy of x, knowing that this. So this is like, given that y is equal to y, so I condition the distribution over y being equal to a particular value, and then I look at the entropy of x in that particular case, right, on the distribution p of x, given that y is equal to a particular value, and then I take the expectation over y. And this, again, if you work out what this is equal to, this is going to be the sum over xy. We have some joint distribution between x and y, and we have the log of p of x given y. And another fact about this is that this can actually be written as h of xy minus h of y. And here h of xy, all I mean is that I'm going to consider xy as one big random variable, so it has an entropy as its own thing, minus the entropy of y by itself. Like you can just work this out from the expression. And there's also a quantity called the mutual information. Which is, again, given two random variables that are potentially correlated, the mutual information between x and y, defined as h of x minus h of x given y. So it's basically, you look at the amount of information there is in x by itself, and subtract the amount of information there is in x given y. Right? So basically, if you know y, by what amount do you reduce the entropy, the amount of uncertainty you have about x? So the more correlated x and y are, the more knowing y should reduce the uncertainty you have about x. Right? So this is sort of the motivation of the behind this definition. And it turns out to be symmetric. Again, this is easy to check. So it's equal to the same thing, but you exchange x and y. And this has some pretty natural properties as well. So like if, for example, if x is equal to y, and let's say x and y are random bits, and x is equal to y, then you have that xy is equal to 0. Yeah, that's right. It's equal to 0, and the mutual information is equal to 1. If x and y are independent random bits, then you have the other way around, right? It's like knowing y, you still have one bit of entropy on x. The mutual information is 0, and so on. I know I'm going a bit fast here, but I'm really running out of time here. If you want to know more about this stuff, there's the book by Cover and Thomas, which I highly recommend, like Elements of Information Theory, it's called. Okay, one last property about this is and I'm just going to state it without proof. It's called the asymptotic equipartition property. Commonly called the AEP. And so this is, so suppose that we have now n random variables that are IID, so independent, identically distributed, so x1 to n, IID. Then it turns out that there exists a typical set. I'm going to call it T and epsilon, so an epsilon typical set for some small epsilon here, which is basically a bunch of strings whose probability is almost 2 to the minus n times the entropy of x. So here we have plus epsilon. You have 2 to the minus n x minus epsilon here. And this typical set has some properties. So the first one is that almost everything is in the typical set, or more precisely, the probability of getting, if we generate x according to this distribution, of getting something that's in the typical set, goes to 1, as n goes to infinity for any epsilon. And the second property is that the set is not very big. So it's about 2 to the minus x, plus. If I look at the size of this typical set, bounded these two quantities, again for n large enough. So basically, if we look at the distribution of the strings here, so if we look at all possible values of xn here and the probability, and let's say we order these strings by probabilities, we have a distribution that looks something like this here. Okay, maybe not so sharp here, but basically we have some sort of, that like this would be the typical set here that has roughly proper probability 2 to the minus h of x here. This contains almost all of the probability inside it. So we have like some sort of almost flat distribution over these strings. And then we have a bunch of outliers here, but the probability of the outliers goes to 0 as n goes to infinity. So essentially, if we have an IID distribution, we can treat it as something that's actually just a typical set, which contains only roughly 2 to the n times h of x strings, and it's essentially uniform over this. And this is why the entropy is so useful in information theory. Basically, as soon as we have these IID variables, then we have something it essentially characterizes the number of strings we have up to an event that we can ignore. Okay. Now let's try to get to the quantum case finally. So this was an extremely fast crash course on quantum information, on classical information theory. Now in the quantum case, what happens? So now instead of having a random variable, we have a density operator. We have rho A equals to some, let's say PA A here. And this here is so this is the spectral decomposition of my density operator, which means that the eigenvalues here form a probability distribution. And then what I can do, suppose now I want to define the entropy of A over the density operator rho. So the density operator plays the role of the distribution in the classical case. So and then the Hilbert space HA plays the role of the set stripped X that I had in the classical case. It's the notation H of A over the distribution rho. And this is just going to be the entropy of the eigenvalues. This is how I'm gonna define it, like the classical entropy of the eigenvalues. So this is just going to be this, right? So it's going to be the same expression that we had in the classical case, but with PA. And now, suppose I don't want to look at the spectral decomposition. I just want to look at an expression that involves rho. I can write it as minus the trace of rho A log rho A, where again I'm playing the same trick here with applying a function to a density operator. I look at the density operator. I apply a log to the eigenvalues. Then log rho A is going to be an operator again. And if you do the computation, you'll just get this. So far so good. Like this looks a lot like the classical case. It looks like we're going to have it easy, making this all quantum. So let's try to do the next step. So conditional entropy. So now, classically, we had a joint probability distribution over two random variables. The quantum version is that we have a density operator, rho AB, on two systems, A and B. So we'd like to have, to define B rho equal to what? So let's go back to the classical case to see what we should do. And now we see a problem, right? How did we define the classical conditional entropy? We had the expectation over y of this entropy here, given that y was equal to a particular value. And now we hit the problem that's the bane of quantum information theory, namely that we can't really condition on a particular value, right? Like conditioning on the fact that b is equal to a particular value is not something that we can just do, right? Like doing this would somehow involve having to measure b, which changes the system, which messes things up, and it doesn't really make sense, right? So what can we do? Plan B. Let's just define it this way. Right? This we can do. So we had the fact that the conditional entropy between the x's, so x given y, we didn't work out, but we could have worked out that it's equal to this, and this we can, this there's no problem, right? We can just define it like this: h of AB minus h of B. And this is so here. So h of AB is just that I look at row AB as one big system, and I do this. There's nothing stopping me. HB is I'm going to trace out A. I'm going to do the same procedure and compute the entropy. So these two things are perfectly well defined. Now, what happens? Like, are we out of the woods here? Does everything work out? There's one bizarre fact that we get now. So in the classical case, I didn't write it, but this year was always non-negative, and it's not hard to see this, right? From this expression, each of these terms here inside our expectation was non-negative because it's the entropy of some distribution that we have a convex combination of a bunch of non-negative terms, which means that the conditional entropy has to be non-negative. And here, this is not the case. This can be negative here. Why? Well, consider rho AB equal to phi AB. So, or let me write it properly. So it's phi like this. So maximally entangled state between AB. And suppose they're qubits, right? So now h A given B is equal to h of AB minus h of B. H of AB, this is a pure state, so its spectral decomposition is this here. So it's we have a single term with a 1, and everything else is 0. This is basically the distribution of a random variable that's always the same value, which means it has entropy 0 here. HB here, if we trace out A here, we saw as one of the properties of the state is that if we trace out one of the two states, the other one is the maximally mixed state. So it's something that's a uniform distribution over B. So a uniform distribution, if B is a qubit, then it's going to have an entropy of 1. So we get -1. That's our conditional entropy. So already, this puts a wrench into our whole interpretation of this as a measure of uncertainty, right? Because now the uncertainty of A given B is negative. So we have a negative uncertainty about A. So it's not so clear how to interpret this. So if I don't run out of time, we'll see how we can interpret this, but no, it's not so clear we'll get there. And then just to complete the picture, we can also have define the mutual information, again formally by just having, so if I have a state rho AB, the mutual information between A and B, you can just define it as h of A minus h of A given B. And this actually turns out to be always non-negative. So I guess I didn't say this in the classical case, but there's always, we know that h of A given B is always less than or equal to h of A. And effectively what this means is that if I gain if I gain information B about A, then I certainly can't increase my uncertainty about A. This fact remains true quantumly, even if this thing can be negative. So, but this is always true. Okay, I had something about the asymptotic equipartition property in the quantum case, but I'm going to skip this as well. So basically, the upshot is that this typical set here, classically, in the quantum case, it becomes a typical subspace. Because basically you do this whole trick, you look at, you have the distribution over the eigenvalues. You look at, if you have row tensor n, you're going to have a bunch of strings in there. You look at the a1 to n that are going to be in the typical set. Take the span of that, and that becomes a typical subspace. And then it has the same properties essentially. I guess I'm just going to skip that to go into some results that we have in quantum channel theory. So I'm going to get back to the problems I was talking about at the very beginning of the talk. I think I'll just go straight to channel coding. So back to information theory. Or information theory problems, rather. So channel coding, and let's just look at the IID case. So here the IID case was the problem. The basic problem was the following: like we had a channel, quantum channel. We had n copies of it. So imagine that we have the same channel that we can use n times. And then we had what we wanted to do was to send some bits or qubits over the channel. So we had an encoder and a decoder. Gonna run out of space here. Now, so we had. Let's say we look at the classical case. Right? Let's say we want to send classical data over our quantum channel. So. Data. Then we have hat here, and now what we wanted is for every m in the set of messages that we want to send, right? So here we have a m script m here is the set of messages that we might possibly want to send over our whole system. We want to ensure that the probability that m hat different from m is small. And here, so here the encoder, what it's going to do is it's going to look at what message we're trying to send. For each message we're trying to send, it's going to have a quantum state over the shared inputs to all of the channels here. So there's going to be a big quantum state on A1 to AN that depends on the message. It's going to go through the channel, and then the decoder here is going to be a big POVM. So it's going to look at what comes out of the channel. So V1 to be N, apply one big POVM to it, and then M hat is just going to be the outcome of that POVM. And then we want the probability that M hat is different from M to be as small as possible, and to go to 0 as n goes to infinity, like 0 as n goes to infinity. And of course, we want script m here to be as big as possible. So, and quantify this, we define the rate of a code, and the rate of the code is the number of bits we're trying to send. So the log of the number of messages, of number of possible messages that we're trying to send over our system, divided by the number of channel uses. So the rate is basically the number of bits that we're trying to send per use of the channel overall. Now, we're going to say that a rate is achievable if there exists a sequence of encoders and decoders that on bigger and bigger block sizes. So as n increases, we want that there exists En and dn such that like the error probability goes to 0 as n goes to infinity, and we want the rate, so the rate of the end code in our sequence of code to go to r as n goes to infinity. So if there exists such a sequence of encoders and decoders, then we're going to say that the rate r is achievable. And the capacity, now the capacity of a channel, capacity of n, is the supremum of achievable rates. So now these are all our definitions for this particular problem of sending classical data over quantum channels. And now there's a theorem due to Holevo, Schumacher, and Westmoreland that says that the following expression is achievable. So if I might explain what this is, rho xb is an achievable rate. And here, this max here, so it's overall, so this is the mutual information between x and b over all rows of this form. So rho xb is going to be p of x on x tensor, and then we have so for some set of states sigma x here. So basically we look at one copy of the channel, a single one, and then for every x we're going to have a sigma x that we're going to have that we have in mind here, and we look at we pass it through the channel, create the state here, and then evaluate the mutual information on it. Right? So this is a small optimization problem that can in principle be solved, right? Like if the channel is over like 1 qubit or a few qubits, you can essentially do an exhaustive search on it. It's not too expensive. And this tells us that this is an achievable rate for this problem. And then for many years, there was a big conjecture, which is it was called the additivity conjecture. Is this the capacity? So we knew we could achieve this. Was it possible to do better than this rate? This was open for many years. It's probably the biggest open problem in quantum Shannon theory until we got the answer to it, which is no, by Hastings. So answer no. This is by Hastings in 2008. And basically what he showed was that there exists a channel. Actually, maybe to go back, why was this? What could happen here that's not? I think it's not achievable. So basically, to achieve this this rate, what you have to do is that the encoder essentially, given any set of messages, the state it's going to create at the input is going to be a product state. So it's just going to have a sigma x1 or a sigma a1, sigma a2, like a big product state on it. And then the question is, well, can we do better by having entangled inputs here across all of the channel uses? This was the central question here, as whether this was the capacity or not. If you could do better, you needed entangled inputs. And what Hastings showed is that this is the case. Right? So he showed that there exists a channel N such that the HSW capacity of N tensor 2, so if I take 2 copies of the channel, it's strictly bigger than twice, which is the capacity of a single copy of it. And then that proves that, well, this is not a capacity. You can do better. Now, the depressing thing about this result is that this there exists here really is an existence proof. It's an existence proof only, in the sense that the way it's proven is that you define a probability distribution over channels such that there's a non-zero probability that, like, if you choose the distribution well, there's a non-zero probability of having a channel that violates this, or that achieves this. Here. And we only have that. Like, we don't have explicit examples or anything like that. We know that there are counterexamples. If I look at the other natural questions here about quantum channels, that would be, instead of sending classical data, you would send quantum data. So here maybe I'm just going to recopy my diagram here just to save some time. Would have something like this here, and now what I'm going to have is now I have some state that I want to send, and like I said at the beginning, now what might happen is that I want to send quantum data, which means that M here would be any quantum state over some space. And of course, if I want to transmit quantum data, that means that this quantum data could be entangled with something else. And we have to take this into account in our definition. So what we want here is that whatever comes out here, I'm going to relabel it as M here, so it's going to be sigma MR. So what we want is that the trace distance between MR, so what comes out of this whole thing, and the ideal situation. The ideal situation is that we get back whatever we sent through it, right? So rho MR1 is small. And again, we want the size of M here to be as big as possible. So we want this to be true for all rho MR. And now we can define the quantum capacity as essentially the same way. So we're going to have a rate that's, again, defined the same way. Instead of the size of M here, it's going to be the dimension of M. Achievable rate defined the same way. Again, the capacity is the supremum of the achievable rate. And now we have another achievability theorem, this time by Lloyd, Shor, and Devatak, that says that the rate CLSD, let me write it on a separate CLSD of N is max of rho. And now this is now we really use the fact that this can be negative, right? So it's the maximum of minus h of A given B. So this is achievable. And now this rho AB here is a state that can be produced by this process here. So we can have A, let's say this is A prime B. So this is something that can be like rho AB would be here. So anything that can be produced by, I send A prime through B and I have a system that's correlated with it. So this is an achievable rate. And here you can also ask the question of whether this is the capacity. This was not really a big open problem because we've known for a very long time this is just not true. So CLSD is not the capacity. And it's actually, for this we have much better counterexamples than for the classical case. Like for example, even the depolarizing channel violates this. Like it's even visible for n equals 5. And like if you take the depolarizing channel, and you put the right noise parameter, like with the right epsilon, you take 5 copies of it, and even then you see this. You get a violation. You can even have something called superactivation, which is you can have there are situations where you have channels N1 and N2 where both of them have 0 capacity. And if I put them together, so I take the big channel N1 tensor N2, then you have positive capacity. So you can go from 0 capacity to positive capacity. So there's all kinds of weird things that happen when you look at the quantum capacity of quantum channels. Like even the most basic questions are unknown, right? The capacity of the depolarizing channel. You expect this to be one thing we know, and we don't. The one place where we really do have answers is the case where we have free entanglement between the encoder and the decoder, like in both cases for both classical capacity and quantum capacity. So then, if we have entanglement at the encoder and decoder that they can use to increase their transmission rate, then for classical capacity, the capacity is just this max rho of IAB, where the max is over this type of states, and the quantum capacity is the same thing with a 1/2 in front. Yeah, I guess I just don't have time to go into any of this stuff, unfortunately. So maybe I'm just going to conclude with some pointers on where you can learn more about all of this stuff. So, probably the number one book that you can look at for quantum Shannon theory is a book by Mark Wilde. It's called From Classical to Quantum Shannon Theory. Classical to Quantum Shannon Theory. Yeah. So it's available on the archive, so you can just look it up. Very much recommended. It's got everything you need to know about quantum Shannon theory. One thing I haven't really talked about is so I've basically focused on IID problems. A lot of the reason one of the big active areas of research in quantum information theory right now concerns one-shot problems where we don't have this IID structure. It's also relevant for cryptography, and there. One of the best resources is another book by Marco Tomamichel. And it's called the Quantum Information Processing with Finite Resources, Mathematical Foundations. Again, it's available online. Finite Resources, Mathematical Foundations. So this one is a bit more advanced than the first one. I think I'd recommend having a more solid understanding of quantum theory before going into this stuff. But it's a very good resource once you have the background for it. And on that note, I think I'm going to conclude here. If you have any questions, I'm happy to take them. Thank you again for the invitation.
Thanks a lot for the really nice session.
Thanks. Maybe I can ask a question to
Sure.
start. So for the case of the quantum capacity, we can have an arbitrary gap when we take multiple copies. I mean, it could be 0, and then when we take multiple copies, the corresponding coherent information quantity becomes positive.
Yes.
But this, I guess, cannot happen in the classical case. Right? Do we have bounds for how much, like how large additivity gaps there can be in the? in the classical case?
In the classical case, I don't think we know much about this, right? Like what we know are, again, these existence proofs that show a tiny gap. And I don't think we even have explicit counterexamples of it, right? So the classical case is very, very poorly understood, I would say. Yeah, in the quantum case, there's much more known about at least the gap. Like for example, the superactivation can happen after an unbounded number of copies. Like we have examples where, you know, for n copies, it's the capacity is 0, and for n+1 it's positive for any n. Yeah, I don't know if I.
Good. Thanks.
There's a question in the chat as well,
Yes.
about the interpretation of negative entropy.
Right. So what meaning do you get to a negative quantum entropy? Well, again, right, like you can see a meaning for it here, right? Like yeah, I don't think I have a very intuitive answer for it, right? Like this negative entropy, like the negative of the entropy actually characterizes some protocols, some quantities in this way. So that effectively you need entanglement to see negative entropy, and basically so you can turn it around and view it as a measure of entanglement, essentially. That's why it shows up in this LSD capacity of a channel. Of course, if you want to stick to a really intuitive interpretation of it, then you have to give up the fact that it's an amount of information, right, or an amount of uncertainty, because it's negative. It just doesn't make sense, right? So you have to fall back to how well it characterizes some operational tasks, such as channel capacity. This entanglement distillation also that's characterized by this quantity. So yeah, you can fall back on things like that. Another question for the additivity conjecture: has there been any recent development to find concrete examples? I'm not aware of any. I'd be interested in. I mean, maybe I missed something, but I'm not aware of explicit counterexamples. I mean, it'd be very interesting to see one, right? Because of course, once you know that this quantity is not additive, then the obvious question is, what is the capacity that's not that? Right? Is there a simple expression that characterizes the quantum capacity or the classical capacitive quantum channels? And we don't even really have candidates for it. Like a candidate quantity that we would conjecture is the capacity. We don't even have this now. So yeah, no, it's a very tough question.